Good morning to one and all. This is Dr. Padma, Assistant Professor, Department of Physics, Institute of Aeronautical Engineering. Today our topic is tunnel diode. The topics to be covered in this session are volt ampere characteristics of a tunnel diode, symbol of tunnel diode equivalent circuit of oscillator, negative resistance amplifier theory, performance characteristics and its applications. These are the topics. What is tunnel diode? So tunnel diode is a specially made PN junction device which exhibits negative resistance over part of the forward bias characteristics. So tunnel diode is also a specially made PN junction diode. So tunnel diode is also specially made PN junction diode which exhibits negative resistance. So which exhibits negative resistance over, if you take any part of the forward bias characteristics, it shows the negative resistance. So tunnel diode is a specially made PN junction diode which exhibits the negative resistance over any part of the forward bias characteristics. So it is extremely heavy doping on both sides of the junction. So for example, this is PN junction. So left side is P type, right side is N type. So the heavy doping on both sides of the junction. So P type and N type both are heavily doped. So it has extremely heavily doping on both sides of the junction and abrupt transition from the P side to N side. It take a abrupt transition from P side to N side. So the tunneling effect is a majority carrier effect and is consequently very fast. So tunnel diode is a specially made PN junction device which exhibits the negative resistance while we are taking any over the part of the forward bias characteristics. So it is extremely heavily doping on both sides of the junction. That means P side and N side both are heavily doped and take a abrupt transition from P side to N side. So the tunneling effect is a majority carrier effect and is consequently very fast compared to the normal PN diode. Compared to normal PN junction diode, the tunneling effect is a majority carrier effect and it is consequently very fast compared to the normal diodes. The tunnel diode is useful for the oscillation or amplification purposes. So generally tunnel diodes are used for the oscillation or amplification purpose. Because of the thin junction and a short transit time, it is also useful for microwave applications. So these are mainly used as fast switching circuits. So tunnel diode is useful for oscillation or amplification purposes. Because of the thin junction and short transit time of the tunnel diode, it is very useful for the microwave applications. Those are used as fast switching circuits. Volt ampere characteristics of a tunnel diode. Volt ampere characteristics of a tunnel diode is nothing but VI characteristics of the tunnel diodes. So volt means V, ampere means I. VI characteristics of a tunnel diode. So these two figures represents the volt ampere characteristics. So from this figure we observe that this one is the forward bias region, this one is the reverse bias region. So here VP is the voltage. So here IP and VP are the peak point parameters. So here IP means peak current, VP means peak voltage, and IV, VV are the valley point parameters. So here two reasons are observed, that one is the peak, second one is the valley. Here IP and VP represents the peak point parameters. Those are the peak current and peak voltage, and VV and IV are the valley point parameters. So peak point to valley is a point negative resistance. So it is a peak point to valley is the point negative resistance. Here the resistance will be negative. So in this figure also, this is the tunneling current, this is the injection current. Tunneling current and injection current both are observed from the figure 2. So sum of the tunneling and injection, V is the VI characteristics of the tunnel diode. So from figure 1 it is observed that here one observed that one peak and one valley. Here IP and VP are the peak point parameters and IV and VV are the valley point parameters. From figure 2 we observe that the tunneling current and injection current in forward bias region. So the tunnel effect controls the current. The tunnel effect controls the current at very low values of forward bias. So if you take any low values of forward bias voltage is VF. So the tunnel effect controls the current at very low values of the forward bias, where the normal or the injection current is very small. At that time, the normal current or the injection current is very small. So the mechanism of tunneling is a purely quantum mechanical phenomena. So tunneling is a quantum mechanical phenomena. So electron on one side of the barrier will have a certain probability of leaking through the barrier if the barrier is very thin. For example, if you take PN junction diode, here P side, this is the N region. Here one region is there, that is a potential barrier. So this is called potential barrier. So an electron on one side of the barrier, for example, the electron is present in the N side. So it take a certain probability of leaking through the barrier if the barrier is very thin. For example, this potential barrier is very thin, then the electron is directly diffused or directly tunneled to the P region if the potential barrier is very thin. So an electron on one side of the barrier will have a certain probability of leaking through the barrier if the barrier is very thin. So the potential barrier is very thin, then the electron from one side to other side it will easily tunnel. Tunnel means it is easily penetrated through the very thin layer of the potential barrier. If both P and N type materials of junctions are heavily doped, the depletion region becomes very narrow. So if P type region and N type region, those junctions are heavily doped, means the depletion region thickness is very small. So as narrow as of the order of the 100 angstroms. So the depletion region thickness is 100 angstroms. So the tunnel effect controls the current at very low values of the forward bias, where the normal or the injection currents are very small. So the mechanism of tunneling is a purely quantum mechanical phenomena. So an electron from one side of the barrier will have a certain probability of leaking through the barrier if the barrier is very thin. So if both P-type and N-type regions are heavily doped, then the depletion region becomes very narrow as the order of 100 angstroms. So another effect of heavy doping is to widen the donor level in the N material and the acceptor level in the P material respectively. So another effect of the heavy doping, due to the heavy doping, the other effect is it widens the donor level in the N type material. If you take the N type region, it widens the donor level, and if you take the P type material, it widens the acceptor level in the P type material respectively. So the Fermi level also moves up into the conduction band in case of N-type material and moves down into the valence band in case of P material. So the Fermi level also moves. If for example, this is conduction band, this is valence band. In between conduction band and valence band, one level is there, that is called Fermi level. So if you take N-type material, means the conduction level moves upward direction. If you take P-type material, means the the Fermi level moves downward to the valence band. So the Fermi level moves upward direction into the conduction band if you take the N-type material, and if you take the P-type material, the Fermi level moves downward into the valence band. So this is the symbol of the tunnel diode. So which shows the symbol of the tunnel diode. This is positive P region and this is negative. So this works as anode and it will works as the cathode. Positive and negative. So this is the symbol of the tunnel diode. Then the energy band diagram of the tunnel diode. So the resulting energy band diagram of the heavily doped unbiased. Unbiased means it is a zero biased. There is no voltage applied. Zero biased PN junction is shown in the figure. So the resulting energy band diagram of the heavily doped unbiased PN junction is shown in this figure. From this figure, it is observed that this is the conduction band, EV is the valence band, EF is the Fermi level. So this one is valence band, the conduction band. So one side region is the P side region, this one is the left side is the P side region, and right side is the N side region. In between P side and N side, so the space charge region is formed. The space charge region is formed. These one are the field states. So that is the energy band diagram of the heavily doped unbiased PN junction. So under unbiased condition, under unbiased condition means zero bias. So under unbiased condition, there is just the same probability of electrons going from states in the conduction band on the N side to the states to in the valence band on the P sides as in the opposite directions. So net tunneling on the thin barrier is then zero as shown in this figure. So under zero bias condition, there is the same probability of electrons. If you take electrons, those are going from the states of the conduction band on the N side to the states in the valence band on the P side. Both are opposite direction and same quantity. That's why here the net tunneling on the thin barrier is zero as shown in this figure. So here the tunneling is taken from this direction. So here this one is the zero bias condition. So the probability of the electrons, so on both sides from N side and P region is same and opposite direction. That's why the net tunneling on the thin barrier is zero for unbiased condition or zero bias condition. So if you apply the forward bias, so the forward bias is applied, then energy levels on the N side are raised. So the energy levels on the N side are raised relatively on P side, and consequently the electrons in the conduction band on N side see empty states just across the barrier and tunneling takes place. So under zero bias condition, there is no tunneling. But if you apply the forward bias condition, so the energy levels on the N side are raised relatively those on the P side. So the energy levels on the N side is raised relatively as the P side, and consequently the electrons in the conduction band on the N side see empty states just across the barrier and tunneling takes place. Here the tunneling takes place. So this tunneling current will read a maximum value IP. So the tunneling current value is IP at a forward bias of Vp of the order of 0.1 volt as shown in this figure. So the tunneling current will read a maximum value of IP at forward bias Vp as the order of 0.1 volts as shown in this figure. As the forward bias is further increased, the energy levels on the N side are raised so high that only part of the electrons in the conduction band see available energy levels across the barrier. So as the forward bias is further increased, the energy levels on the N side are raised. So the only part of the electrons in the conduction band available energy levels across the barrier. The tunneling current is reduced as the bias increases. So the tunneling current will be reduced if you increase the bias. This phenomena, the suppression of tunneling process is responsible for the negative resistance part of the diode. So tunnel diode means it shows the negative resistance over the part of the forward bias characteristics. So this phenomena is the suppression of tunneling is responsible for the negative resistance from the part of the diode characteristics. At the bias, VV is entirely made up of ordinary injection current. So the bias VV is entirely made up of the ordinary injection currents. Between the peak currents IP and valley currents IV. IP is the peak current and IV is the valley current. A negative dynamic resistance R equal to dV by di is obtained. Here we obtain the negative resistance, that is R equal to dV by di. Beyond VV, the current rises again because of the injection currents in an ordinary PN junction diode reaching a value of IP at a voltage of VF. So beyond VV, so the forward bias current, the current rises again because the current rises due to the injection of the currents in an ordinary PN junction diode reaching a value of IP at voltage of VF. So the third case is reverse bias. If reverse bias is applied, the height of the barrier is increased. This is the barrier height. Compared to forward bias, here the barrier height will be increased above the open circuit value E0. So E0 is the open circuit value. If the reverse bias is applied, the height of the barrier is increased above the open circuit value E0 as shown in this figure. We now observe that there are some energy states in the valence band. So there are some energy states in the valence band of the P side which lie at the same level as allowed empty states in the conduction band of the N side. So conduction band means it consisting of empty energy states. So valence band means it is a filled states. Now we observe that there are some energy states in the valence band of the P side which lie at the same level as compared to the empty states in the conduction band. Here we observe that the EF lies in between EC and EV. Hence, these electrons will tunnel through from P side to the N side, giving rise to the reverse diode current. So, the electrons will tunnel through from P side to N side. So, the tunneling is taken from P side to N side. P side to N side, it giving rise the reverse diode current. It may be seen from the above diagram. As the reverse bias is increased, the diode current increases. If you increase the reverse bias, the diode current increases. Hence, the tunnel diode behaves as a good conductor when reverse bias is applied. If you apply the reverse bias, then the tunnel diode acts as a good conductor. While we are applying the forward bias, we will see the negative resistance. So, most commercial tunnel diodes are made of germanium or gallium arsenide. Since high peak to valley current ratio, IP by IV is difficult to obtain with the silicon. That's why we are using mostly the tunnel diodes are fabricated with germanium or gallium arsenide. So, if reverse bias is applied means the height of the barrier is increased. Now, the tunneling takes place. If you increase the reverse bias voltage, then the reverse bias current is also increases. Hence, the tunnel diode behaves as a good conductor when we are applying the reverse bias. Tunnel diode equivalent circuit of oscillator. So figure shows the equivalent circuit of an oscillator. Here C2 is made larger than C1. C2 is greater than C1. C2 is made larger than C1. Capacitive tapping is more suitable to inductive type as the latter produces spurious made of oscillations. So here RJ is the junction resistance. CJ is the junction capacitance. Capacitance RS is the series resistance. L is the inductance. So here the equivalent circuit of an oscillator represents that here C2 is made larger than C1. Capacitive tapping is more suitable to inductive tap as the latter produces the spurious made of the oscillations. Tunnel diode. So coupling of the diode to the cavity or resonator and coupling of the bias circuit are two practical important considerations. So for high Q circuits, the equivalent parallel resistance is RP. So RP is the parallel resistance. So coupling of the diode to the cavity or resonator and coupling of the bias circuit, coupling of the diode to the cavity or resonator and coupling of the bias circuit are the two practical important considerations for the tunnel diode. For high Q circuit, the equivalent parallel resistance RP is given by Rp equal to 1 by omega square C2 square into R1. So if Rp decreases as C2 increases, so if you increase the C2, increase the C2, then Rp will be decreases. Rp will be decreases when the negative resistance greater than the Rp oscillations will stop. So this is because the capacitive tapping act as a transformer for the diode negative resistance. Further, the DC is applied to the diode should not interfere with the tuned circuit as already mentioned, since coupling with the help of circulator is quite extensive and complicated. A simple bias filter which avoids the circulator is often used. Basic circuit of a tunnel diode oscillator is shown in this figure. This is the bias filter. This one is the tunnel diode. So if Rp is the parallel resistance, Rp equal to 1 by omega square C2 square by R1. If Rp decreases, if you increase the C2 when the negative resistance greater than the Rp oscillations. This is because the capacitive tapping act as a transformer for the diode negative resistance. Further, we apply the DC bias is applied to the diode should not interfere with the tuned circuit as already mentioned. Since coupling with the help of a circulator is coupling to the help of circulator is a complicated process. Negative resistance amplifier theory, which is applied to the tunnel diode. So negative resistance amplifier theory. So in a feedback oscillator, as per Barkhausen criterion, A beta must be at least unity. A beta must be at least unity as per the Barkhausen criterion. In a negative resistance oscillator, two sufficient power gain does exist as the negative resistance makes all the losses. So a tunnel diode certainly behaves as one. So a negative resistance amplifier using a suitable representation for a tunnel diode is shown in this figure. Here GS is the conductance. GS is the conductance. Here G is the tunnel diode. So in a feedback oscillator, as per Barkhausen criterion, A beta must be at least unity. In a negative resistance oscillator, two sufficient power gain does exist as the negative resistance makes up all the losses. So a tunnel diode certainly behaves as one. So it consists of a input current source. So the tunnel diode consists of a input current source is with a source conductance GS. GS is the source conductance connected to a negative conductance G. So GS is connected to negative conductance minus G as shown in above figure. So here GS is connected to minus G. So it consists of a input current sources with source conductance GS. GS is the source conductance that is connected to a negative conductance G. GL is the load conductance. So here GS is the series conductance and GL is the load conductance. GL is the load conductance. So it consists of an input current source is with the source conductance GS is connected to a negative resistance G. GL is the load conductance. If frequency operation is not high RS is the series resistance, LS and CJ can be neglected from the equivalent circuit of the tunnel diode, marking minus G as a suitable representation for the tunnel diode. So if frequency operation is not high RS means series resistance, LS and CJ can be neglected from the equivalent circuit of the tunnel diode, marking minus G as a suitable representation for the tunnel diode. So in the absence of the diode, the maximum power from the generator P maximum equal to IS square by 4GS. So the maximum power from the generator is represented by P maximum equal to IS square by 4GS. So with the diode present, VL equal to IS by GS minus Z plus GL. So with the diode presence, so with the presence of the diode, VL equal to IS divided by GS minus G plus GL. Thus the power delivered in the load is PL, power delivered in the load PL equal to VL square into GL, that equal to GL into VL square means IS square divided by GS minus G. So in the place of VL we can substitute PL equal to VL square into GL, that equal to GLIS square divided by GS minus G plus GL whole square. Why? Because here VL value is IS divided by GS minus G plus GL. So power again AP due to the presence of diode. So power again power gain AP. So AP is the power gain. Power gain AP equal to PL divided by P maximum. PL value is IS square into GL. So PL value is IS square into GL divided by GS minus G plus GL whole square. That is the PL value divided by P maximum value is IS square by 4GS. 4GS. So from this AP equal to power gain, AP equal to, so 4GS into GL, IS square cancel. So GL, 4GS into GL divided by GS minus G plus GL whole square. So that is the power gain AP equal to 4 into GS GL divided by GS minus G plus GL whole square. That is equation 2. So for maximum power transfer, the load and generated conductance are equated, and it is easy to prove that 1 by AP is less than 1 instead of proving AP is greater than 1. So for maximum power transfer, the load and generated conductance are equated, and it is easy to prove 1 by AP is less than 1 instead of providing AP is greater than 1. So 1 divided by AP equal to, already we know that AP value is 4GS into GL divided by GS minus G plus GL whole square. So 1 divided by AP means GS minus G plus GL whole square by 4 into GS into GL, that equal to 2GL minus G whole square divided by 4GL square. So 4GL square minus 4GL into G plus G square divided by 4GL square. So by dividing with 4GL square, we can get 1 plus G square minus 4GL into G by 4GL square, that is equation 3. So in the second term of the equation 3 is negative if AP is less than 1, that is 4GL is greater than G. Under these conditions, 1 by AP is less than 1 and thus AP exceeds unity. So in the second term of the equation 3 is negative, AP is less than 1, that is 4GL is greater than G. Under these conditions, 1 by AP is less than 1 and thus AP exceeds unity. So hence the real power gain is available. Since the circuit has power gain, it may be used as an amplifier. Care should be taken so that 1 by AP expression is not reduced to 0, which would happen for a value of G such that last term must be equal to minus 1. This would occur when G equal to 2 into GL. So it is thus seen that an amplifier containing a negative resistance is capable not only for the power gain but also infinite gain. So hence the real power gain is available. Since the circuit has power gain, it may be used as an amplifier. Care should be taken so that 1 by AP expression is not reduced to 0, which would happen for value of G such that last term equal to minus 1. So this would occur when G equal to 2 into GL. So it is thus seen that an amplifier containing negative resistance is capable not only for the power gain but also infinite gain. So this occurs when G equal to 2GL and it gives the lower limit for the value of G and hence the upper limit for the value of the negative resistance. So if this negative resistance amplifier is capable of power gain, if it is outside these limits should be AP is less than 1 or else it becomes negative. and oscillations can take place. Hence, the power gain considering Cj is given by AP equal to 4 into Gs into GL divided by Gs plus GL minus G plus J omega Cj whole square, that is equation 5. So, the negative resistance occurs when G equal to GL and it gives the lower limit for the value of G and hence the upper limit for the value of the negative resistance. So, if this negative resistance amplifier is capable of power gain, if it is outside these limits, AP is less than 1, or else it becomes negative and oscillations can be taken place. The power gain considering Cj is given by AP equal to 4 Gs into GL by Gs plus GL minus G plus J omega Cj whole square, that is equation 5. So this gives a resistive cutoff frequency or figure merit for such a diode for which magnitude omega Cj equal to magnitude of minus G. So the magnitude of omega Cj equal to magnitude of minus G. So past this frequency, the negative resistance of the tunnel diode disappears. This frequency is given by G equal to omega R into Cj, R equal to 1 by omega R Cj. So G is the conductance. Conductance means the reciprocal of the resistance equal to the reciprocal of the conductance. R equal to 1 divided by omega R into Cj. Or omega R equal to 1 by R into Cj. From this F, omega equal to angular frequency omega equal to 2 pi F. So the frequency F equal to 1 by 2 pi R Cj. So the equation 6 is gain bandwidth product. So the tunnel diode is generally loosely coupled to the tunnel circuit by a capacitive divider or by a filter which prevents the diode from being short circuited by the supply source. So if your tunnel diode is generally loosely coupled to the tunnel circuit by using capacitive divider or by filter which prevents the diode from being a short circuited by supplying the source. This ensures that no positive resistance interfere with the negative resistance of the diode. So performance characteristics and applications. So the major advantage of tunnel diode oscillator is that microwave oscillations of modest power has to be obtained from very simple circuits. So by using very simple circuits, we obtain the modest power for the microwave oscillations. So wide range of tunneling, either mechanical or electronic, is possible. So for low power applications, they are fast replacing reflex klystrons. So another advantage is their low noise. So tunnel diodes has low noise. So the major advantage of tunnel diode oscillator is that microwave oscillations of the modest power has to be obtained from a very simple circuits. So wide range of tunneling, either mechanical or electrical, is possible. So for low power applications, they are fast replacing reflex klystrons. So another advantage is their low noise figures. So other performance characteristics are listed as below. Power is 750 watts, frequency range is up to 100 gigahertz, tuning range is 1 to 4.3 gigahertz, stability is 1 in 105. Because of their low cost and simplicity of the circuits, tunnel diodes are still being used in competition with bulk effects gallium arsenide devices. These are the performance and characteristics of the tunnel diodes. So these are the references for the semiconductor devices, SMG, Dr. M. Kulkarni, Microwave and Radar Engineering. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.